Hello, and welcome back to our discussion of Unit 6, Inferences and Conclusions from Data. In this segment, we'll be taking a look at the normal distribution. Brian, what is a normal distribution and why is this important to study?
Well, James, frequency distributions come in many different forms. Students are familiar with tables and they are familiar with histograms, which is probably the primary way that students view data and summaries of data. So if we take a look at histograms for a second, the histograms that we look at here are basically two different types of histograms. One is a height and the number of men. Could be a relative frequency distribution. It could be just a regular frequency distribution. And normally they are nice, neat bars and things like that. And we end up with, again, a nice description of the data. The one on the left there looks like it's a nice symmetrical kind of a distribution. The one on the right looks like it's kind of a little bit more of a skewed left distribution. What we go to now in Algebra 2 is we look at the normal distribution.
And sorry to interrupt, I was just going to go ahead and draw in, just in anticipation of what's going to go on next, looking at how those bars can be approximated by a curve. And here we have the actual normal curve.
Okay, now the normal distribution is a special frequency distribution that occurs in everyday life. For example, if I were to look at the height of 15-year-old females, and that frequency or relative frequency, it would be normally distributed. If you look at a gallon of milk and it says 1 gallon on it, then that's going to be, again, the distribution of the actual amounts of milk in the jugs that are produced will actually be normally distributed. Normal frequency distributions in almost every case deal with continuous variables instead of discrete variables. And also, and we'll talk about this later, normal distributions play an important role in sampling, and when we talked about making inferences, it becomes extremely important when we talk about inferential statistics.
Brian, what are some of the characteristics of a normal distribution? When you look at a data distribution, how do you know you've got a normal distribution on your hands?
All normal distributions and their curves have many characteristics that are common to all of them. The first point is that the highest point in the distribution always occurs at the mean and the median and the mode. That center reference line is where the mean, median, and mode occur. Okay. The graph also has a vertical axis of symmetry at that same value. You'll notice if we draw a line right down the center at that mean, you'll notice that we end up with a symmetry around that vertical line. Okay. That curve looks like kind of a different curve than what we've seen before, though it is actually a combination. It's an exponential function with an exponent that is a quadratic function. And you'll notice it kind of has both of those characteristics. It has asymptotic behavior near the axes, and it also has almost, in some ways at the top, a parabolic kind of shape. So if you remember in Unit 4, when we studied graphs of combinations of functions, that's where that comes in here. Okay? The equation of that curve, okay, is based on two parameters, the mean and the standard deviation. The mean is going to locate the center, while the standard deviation, as we remember from Algebra 1, determines the spread of the data from the mean. But again, anything that's normally distributed will have this type of curve, this type of view. And James has written the symbol for population standard deviation. Okay, and the population mean, we also give the Greek letter as the letter mu. There you go. Okay, the curve, we like to call it bell-shaped. And you'll notice some percentages on that curve. Those percentages represent areas. And the areas represent the percentage or the proportion of the population that falls between any 2 points on that horizontal axis. So for example, where you have the mean of 0 and 1 standard deviation from the mean, you'll notice the number 34%. Well, that 34% says that 34% of the population in a normally distributed curve is going to fall between the mean and one standard deviation on one side. Now, obviously, if we talk about one standard deviation to both the right and the left, you'll notice that becomes 68%. It's a common number that we use in statistics. It's an approximate number. It's actually closer to 68 and a small fraction percent, but we use 68. Okay? You'll notice the percentages that, because that curve is decreasing from left to right and also from right to left. Okay, the percentage of the population that falls between 1 and 2 standard deviations is 13.5%. Between 2 and 3 standard deviations from the mean is a little bit more than 2%, 2.35%. And then you'll notice that anything out beyond 3 standard deviations, and that curve actually does go to infinity, there's only 15%, 0.15%, I apologize, of the population that is more than 3 standard deviations from the mean. So that's going to tell us a lot of things what's going on here. We also now talk about, we have the 68%. A lot of times you'll hear what's called the 68, 95, 99.7 rule. And the 68 basically says that 68% of the population falls within 1 standard deviation on either side of the mean. 95% falls within 2 standard deviations of the mean, and 99.7% fall within 3 standard deviations of the mean. So again, hopefully what you'll notice is once you get out beyond 3 standard deviations, if a population is normally distributed, you're not going to find too many members of the population out in that range. Okay. Yes, James.
Brian, statisticians talk about z-scores. What are z-scores and how are they used?
Okay, well, let's look at a couple of things here. Let's take a look at an example of a bottle. The bottle says it has 1 liter, which is actually 1,000 milliliters, so we're going to assume that that's going to be the mean. And if I'm manufacturing bottles, what I'm going to see is that I hope that the mean amount is 1,000 milliliters. If it's not, then we have issues, and we'll talk about that when we talk about sampling. We're also going to make the assumption here that there's a standard deviation of 20 milliliters in the production. So what that's going to give us here is it's going to give us a value where the standard deviation from the mean is 1, an actual value of 1,020. Where standard deviation is 2, obviously it's 1,040. And we'll simply keep going for each standard deviation, 20 milliliters up, and of course 20 milliliters down. So that becomes 980 and 960 and 940 if I do the subtraction correctly. Okay. Now, before we talk about the z-scores, let's talk about a couple of things here. For example, let's say I'm interested in what proportion of these bottles are filled to between 1,000 milliliters and 1,040 milliliters. Okay. Okay. So now if I look at the area under the curve for that range from 1,000 to 1,040, you'll notice I have a 34% and a 13.5%. So if I add those two together, what that's going to tell me is that approximately 47.5% of the bottles will be filled between 1,000 milliliters and 1,040 milliliters. Let's say that I'm interested in the percentage of bottles that are filled to, let's say less than 960 milliliters. And again, if things are working well in the factory, you shouldn't get too many bottles that are there, but you will get some. Well, again, we have those two percentages, which is 2.35% and 0.15%. And if I add those two, I get 2.5%, 2.5%. So 2.5% of all the bottles in this situation should be filled somewhere less than 960 milliliters. So now, again, and you can compute these percentages. You can simply, again, replace the mean with whatever the value is. There's use the standard deviation to apply other values, and then that will give a lot of information about the actual fill of the population of the bottles in this case. If we now want to talk about z-scores, we certainly can. Keeping the same situation here, z-scores simply tell me how many standard deviations a particular score is from the mean. If we take a relatively simple example, for a bottle that is filled to 1,020 milliliters, okay, it has a corresponding z-score of +1 because that value is one standard deviation from the mean.
Hey, Brian, could you talk about how a student would compute that z-score of 1? What's the process to come up with that?
Well, the process to come up with that, we have a handy-dandy formula. And of course, if people like formulas, they can use the formula. You'll notice the formula there talks about the z-score is taking the data score, subtracting the mean. So in this case, it's 1,020 minus 1,000. And then dividing that by the standard deviation, which is 20. And so if I do all those computations, do them well in my head, I find that I get a value of +1. The positive number is important because it tells me that that value is one standard deviation above the mean. If I were to go down, for example, let's say to 960, okay, and James will let me pause for a second, let James finish putting that little explanation down. That's good. Let's say if I talk about 960, okay, that is going to be obviously 960 minus 1,000 over 20, which in this case gives me a value of -40 over 20, or -2. Now, one of the things we do have to realize here is that the bottles aren't going to be filled to nice, neat multiples of the standard deviation. You may have a bottle that's, let's say, we might be interested in, less than 970. Okay? Well, we can, by using technology or tables, actually determine that area. The concentration in Algebra 2, for the most part, is just using these basic values with whole number values of standard deviations, though there is instruction as to how to use tables and how to use the calculator to come up with values that are non-integer multiples of the standard deviation from the mean. So it's one of the main uses. Again, if I were, if I get a bottle, let's say I get a bottle and the bottle has, let's say 900 milliliters. Well, if I have 900 milliliters and I compute a z-score of 900, okay, do a little bit of quick calculations here, and I find that I get a z-value of -5. Well, remember, if we look at our standard deviation, our standard normal distribution, we know that there's not too many values that are going to be less than 3 standard deviations below the mean. So if I have a bottle that's 5, that is quite unusual. And maybe if I get a bottle with 900 milliliters, I mean, whoa, hey, I think I'll have to take that back and maybe get a replacement. Okay? So it's one of the important things that we do with z-scores. It can also be used, and it can be a topic for another time. We can talk about comparing two disparate groups and compare them, an individual's score relative to their group. And again, that's something that's also in instruction here. So that's how z-scores are actually going to be used.
Excellent. Brian, thanks for that helpful discussion of what the normal distribution is, as well as what z-scores are and how they're used.
You're welcome.
In the next segment, we'll take a look at the topic of sampling, and we'll see you then.